Okay, everybody, here's the second of the bunches of questions that I'm going to go through with you from your recent measurement and uncertainty test. Right, these questions are just strange, all sorts of odds and sods about weird measurements and calculations, but we'll do them. Right, you have an octagonal pencil, that's what it looks like in cross-section. You've got its width, you've got the diameter of the round bit in the middle containing the graphite. Okay, so they've told you here, why did they use a micrometer to measure the width, and also they measured it several times. So why did they use that? Well, first of all, you can say that your micrometer produces less uncertainty because it measures to a smaller amount. It's now you're not supposed to say more precise. They don't like that here. They said it's more higher resolution, things like that. The other nifty thing is measuring at several places means you can calculate a mean value that will be more accurate or more reliable. So I think that's okay there. So that's the things to pick up. It's a micrometer. They're measuring at several points. Right, and by measuring at several different places, it also means that you're reducing the random error. Now that's probably the cleverer of the various solutions, reducing random error, because the width may not be constant. That's probably the most intelligent thing to say. Right, then they give you, now this is a nice bit of standard stuff about uncertainties. Here's the students' results. They measured it 5 times. They want you to work out a percent uncertainty. Well, if you're going to do that, it's half the range, which is lowest to highest. So there's your lowest, 7.06. There's your highest, 7.23. That is a change of 0.17. So that's what I put in here for my half the range. Half of 0.17, difference between those two. The average, okay, add them up, divide by 5, you get 7.15. So I get those, I get 0.5 multiplied by the range, divide by the average amount, I will get plus or minus 1.189%. I went for plus or minus 1.2%. The mark scheme said 1.19, but you still got your full marks for saying 1.2. Okay, I don't know. I lose the will to live if I'm doing percents to more than 2 decimals. But there you go. Plus or minus 1.19% or plus or minus 1.2%. That's standard stuff. That's sensible. Then we get into weird. They've told you that on this octagon, the cross section is 0.183 multiplied by the square of the width. So that's not your pi d over 4, your pi d squared over 4. It's 0.83 width squared. All right, so what they're not very clear is use the width that we got from the previous question. Then they said work out the diameter of the graphite bit. So work out the diameter of the graphite bit in the middle based on them telling you that the cylindrical core is 9% of the volume, and then telling you that the area of the hexagonal bit of the whole pencil, is octagonal. Is 0.83 multiplied by the width squared. Well, I thought, okay, I'm just going to say to myself, right, I'm going to think about the volume. I'll work out the volume of the whole thing, and then I'll take 9% of that and work out the volume work out the diameter of the round bit in the middle. I did first of all say, right, okay, I'm not going to say millimeters. I'm going to use meters, and that's because you've got to be really careful, because if you do millimeters and then you're sort of converting between length, area and volume, you get in a mess. So I've just said, right, I'm going to do everything in meters and work from there. So I said, right, okay, let's have 1 meter length just to make it easy. Okay, you got a 1 meter pencil, but I just thought that makes the maths easy. Right, work out the volume. Well, for the whole pencil, it's the area multiplied by the length of 1 meter. So let's say it's that number, 0.83 multiplied by the W squared. Right, I haven't bothered putting the number because I'm only going to use it later on. Now the core volume is going to be 0.83, remember that, and then only 9% of it, 0.09. So that's where that's come from. And then I get the volume of the core. If, in terms of D, the volume of the core is pi d squared over 4. Sorry, I think I said over 2 here. Pi d squared over 2 because D is R over 2. So D squared, it's like, you know, so it's R squared is D squared over 4. Right, then I end up with, rearrange it, I get D is the square root of all this, it's D squared, that's just from rearranging. And I get an answer of that many meters, and then I've just written it in millimeters because that's what they're talking about. So I've just done that. It's just a bit of sort of maths, really. Right, I'll leave that on there. You can read through it, you can look through it again by pausing the video. And then they've got, right, this is the weird one. They're working out, they want you to figure out how about wearing the pencil away. Okay, so they've given us some diagrams to read. They showed, right, figure out how long the pencil is when you started. Right, we have got this vernier scale here. There's your sliding vernier scale. Here's when you work out the length of the pencil to start with. If you zoom in a crazy amount, I did this on the Word file, you can get it to 85.3. So there's 85, 85.1 to 3 is where they're lining up, sort of maybe 85. No, if you look on this, yeah, maybe 85.2. I mean, it doesn't zoom very well when you use Word, but this is looking like, to me, around about the, around about the 0.3-ish. So I've said there 0.3, so using that bit. And then in a further question, they ask you to measure length again for when the pencil's been used. They are really hard to read, these scales, but I got this one as no longer 85, it's now 83, but 83.9. Looking at the vernier scale, it tries to be 0.9, it tries to be up here, 0.9, so that's where I did that one. So I've got my two lengths that way. So just popping back here, right, investigating how long it took to wear. Okay, so 85.3, 83.9. Now it says here they drew 20 lines 25 centimeters long, so yet again another unstandard unit. So 0.25 meters 20 times, and then it had worn down from 85.3 to 83.9 millimeters. Right, so if I pop into here, then they want you to work out how long a line you have to draw to get the length of the pencil down to half. I mean, where this comes from, I don't know. Okay, so I said, right, fine. Right, that's the length of lines they drew. 250 mil multiplied by 20. It's 5 meters is the length of the line they drew. When they did that, the pencil length went down by, the difference between those two, the pencil length went down by 1.4 millimeters. Right, if you're going to get it down to half its original length, you've got to go back to the original length here, 85.3. Right, half the original length, you've got to wear away 42.7 millimeters of your pencil. Okay, so what I said was, well, right, let's just see how long a drawn line we need for each meter, if you like, of pencil shortening. So if I divided there the 5 meters of drawn line by how much the pencil went down, and that's just telling me that I need to draw a line 3.5 kilometers long to get a pencil to wear down by a meter, Well, I'm not wearing it down by a metre. I'm only wearing it down by 42.7 millimetres. So I've just said, right, okay, it's not a whole metre, it's that much. Multiplied the 3.571 by the 42.7, and I get 152.5 metres. Call it 153 metres, and that's their answer. Right, 153 metres of length. It's a weird thing. It's all proportion. You can do it by proportioning and things like this. It's, to my mind, that's maths, not physics, but never mind. You've got that, and then those are, I think, just the scales, and I think we're finished with the darn thing now. Okay, that's good. So there's your pencil. Again, pause the video if you're having trouble seeing what the heck I've done, but I just thought, right, okay, I'll just treat it as a maths exercise. And I said, right, yeah, you could do it. You could do it other ways. You know, you could have said, right, you know, that was, it wore down by 1.4 millimeters when we drew a line 5 meters long. So you could have said, right, well, for it to wear down by 42.7, you could have done 42.7 divided by 1.4 multiplied by 5. Well, that would probably have been a bit quicker. So you could have done it that way instead. So you could have done 42.7 divided by 1.4, and that tells you how many times you'd have to do that. Then you multiply 5 by that, divide that. That's another way, slightly quicker possibly. Right, then we're on to the weird and wonderful magnets. It's not an electromagnetism question, it's just a taking measurements question, so don't panic. Right, you've got 2 ring magnets, you've got a pole here, you set them up so they're opposing each other, so this one will drop down and then it will sort of levitate above magnet A as their poles are opposing. Big D, diameter of the whole shebang, little d, the hole in the middle. Take a cross section through it, it looks like that. Sectional view across XX, good old technical drawing term there. Right, yep, they repel and it stays at a fixed height, it doesn't go anywhere. Then they've given you a digital vernier, so you don't even have to look at the little scaly things now. But if you've got a digital one, you still have to take precautions. Reduce the effect of systematic and of random errors when you're measuring the outside diameter, which is big D, outside diameter of the magnet. There it is in cross section, there's its outside diameter. Well, systematic includes zeros, so that includes zero error or zeroing error, because that's an example of a systematic error. Check, so therefore you check that it reads 0 when the size is 0, so when the jaws are touching in the middle it should read 0, and the digital ones are great, they've got a button that you press that says 0 on it, so you can even start off at one at a different length. But that's what you do, make sure it says 0 when you start, and to reduce random error take lots of readings and work out a mean. So right, precaution to measure random error. Right, measure diameter in several different places and calculate the mean. That does the job. Now, I sort of drew this and then I got the one out of the answers. Right, they've said, how would you measure the internal diameter? Now, if you look at these calipers, they've got these jaws for measuring outside of things, and then these jaws measure inside of things. And they cross over each other. They don't meet up, they cross over. And when they cross over, and then you get 0 when the two are actually, you know, in the same place as each other. So you can measure an internal size with those, right? And what I did was I said, right, well, yeah, you'd get your magnet, and you then get it. Then you'd put it over the jaws, and then make the jaws come outwards until they're touching the sides, meaning that it will look like, ta-da! Oops, it'll look like that. So you've got your jaws on the inside like that, right? And they want you to show the jaws inside the hole and touching the sides of the hole. So you only have to draw that bit. You don't have to draw the whole caliper. You just have to draw the cross section. You have to draw that bit in that position over there, and that's what gets you the answer. Right, now here they are reading the thickness of the magnet. Now again, notice in this first diagram they showed you on the little screen, that's the outside diameter. In this one, they have shown you the inside diameter. So they've actually been showing you all the different readings. You've just got to pick that up, they don't tell you. And then here they're showing you the thickness. So what I said here was, oh right, okay, you have got to now work out the volume of the magnet. Now the magnet is a donut shape, right? It's a circle with a hole in the middle. So to work out the volume of the whole thing, right, we're going to have to be a bit clever. We're going to need to work out the volume of the whole disc and then take away the volume of the hole. And I've just written down here, outer diameter 59.9, inner diameter 19.32, and thickness 12.04 in millimeters. And I've done my usual thing. I said, right, I'm not going to muck about with millimeters. I'm going to do all my calculations in meters. Then I can't go wrong. So the disc volume, it's the area multiplied by the thickness. And again, we're on diameters, pi d squared over 4. So here we go, pi d squared over 4 for the big diameter, for the big D. Then I get this number, meters cubed, right? It's a very small number. And then for the whole diameter, same thing, but use the diameter of the hole. There we go. Okay, and multiplying by the thickness, there's the thickness, the 12.09. There it is. And again, doing everything in millimeters, sorry, doing everything converted to meters. You can't go wrong then. So there's my whole volume. Be careful, 10 to the minus 5, 10 to the minus 6. It's not bigger, it's smaller because it's 10 to the minus 6. Difference, take one away from the other. And what I did was, and I left them with all of these with all of these decimal places when I did the difference, but then I rounded it after I'd worked out the difference. So I ended up with 3.05, and they're okay with that. Calculate the area difference. Oh yeah, the other way you could do it if you chose. Right there, I just worked out that volume and that volume and subtracted this smaller volume from it. The other way you could have done it is you could have worked out the area of that, the area of the small hole, worked out the difference in area and multiplied by the thickness. It would give you the same result. Right, then this is the weirdest question of all. They've said right, they've got the thing balancing and it's at height h, and then right, work out the force between the magnets, right, and sorry, yeah, and work out what the constant k will be. They've given you this sort of, yeah, they said they've discovered that this is the relationship. The force will be k over h to the third, where h is the height of magnet B above magnet A. Now, two criticisms I've got here. First of all, you've got a weird one here because it's, you know, the h is not going to be 0 when the two magnets are touching, so you're going to end up with intercepts. And also, the other thing I don't like about this is that they've said force between the magnets. Well, the force between the magnets is going to be the weight of this plasticine they've been adding to change the mass, but also the mass of the magnet itself. Again, there's no mention of this. So I've just said to myself, all right, well, the force is going to be the massive weight of magnet B plus the weight of the clay that they've added. I don't know why they ignore that, because I don't know. Anyway, I've said, right, describe an experiment to do this. So I've said, really, in terms of the force, it should be weight B plus the weight of the clay is k over h to the third. And I still think that h should be the distance between them, but that's another story. Describe an experiment to test the student's conclusion. Okay, well, it's going to be something along the lines of force and then measuring heights, although they've said that they've done it by halving the height. Okay, so add clay to reduce the height by 50%. Fine. Well, I've said, right, okay, if you want to continue the way they've been doing it, I would say weigh magnet B and using digital scales to measure that. Similarly, weigh the clay that you add to make H drop by 50%. Again, it's weird because surely it should be the difference between them, but and then add, and then so you work out that much clay, figure out the mass of that clay added, and then add more clay to drop it by 50% again. I'm actually going along with that because you've got this H to the third thing there, so this might make it easier to, for your amounts of clay that you're adding and things like that. So measure H with a steel rule, plus or minus 0.5mm steel rules are rather than ordinary ones. Keep doing it until the magnets touch each other. They may not, you may not be able to put enough mass on, but record the mass of clay and the H values, calculate the weight in newtons of the clay and the magnet, so you're going to do multiply by mg, and then if you plot a graph of F against 1 over H to the third, they've asked you to work out your gradient. The gradient should be K. I thought, well, fine, this is just standard stuff. So I think they're doing things like wanting you to say you plot a graph of 1 over H to the third, right, for your F. So F is that, so that's your y-axis, that's your x-axis, and that's it. Again, I really didn't like those last two questions, but they are solvable. You can get the full marks. You just got to sort of switch your physics brain off a bit and just think about maths, in my opinion. So there we go. I shall be able to cut that one short. Pause the video if it's looking impossible and stupid, but that's what I got. It matches the marking scheme. It's done. Right, take care of yourselves. Slightly shorter video, thank goodness. Right, see yous.